Okay, so last time we were in the middle of proving Zaslavsky's theorem, which said that if we have an arrangement in Rn and we want to know the number of regions, then all we have to do is work out the intersection poset and just compute its characteristic polynomial evaluated at -1. And there's some sign here. And if you wanted the number of bounded regions, then all you have to do is compute the characteristic polynomial at 1. And so last time we put a lot of work into understanding this characteristic polynomial for matroids. And so we showed there were 3 formulas. First, the definition of the characteristic polynomial. Then Whitney's theorem gave us a second way of computing characteristic polynomials. And then we also proved this deletion-contraction recursion, which is going to be very useful to us. And having done all of that work last time, then it's going to be pretty easy to prove this theorem, because we're just going to induct on the number of hyperplanes. The point being that we have a recursion for the number of regions and a recursion for the characteristic polynomial, and they basically match up. So if there's no hyperplanes, then you can check that this holds. And now suppose it's true for hyperplane arrangements with fewer hyperplanes than A. Okay? Now, we basically showed that the number of regions satisfied a recursion. The recursion says just compute the number of regions of the deletion plus the number of the regions in the contraction for any hyperplane. Okay. Now these arrangements have fewer hyperplanes, and so we can apply the induction hypothesis and say that this is -1 to the rank of, this is bad notation, isn't it? Rank of A delete H times characteristic polynomial of the let me just say, L is the intersection poset, and M is the matroid. Remember that we only have a matroid when this thing is central, but the same argument works if you assume that A is not central. So maybe we'll prove it for central arrangements and just tell you that the proof works.
Central was that they all go through the origin?
So remember, central means that they're linear hyperplanes that go through the origin. And we said that if the arrangement is central, if everything goes through the origin, then you get a matroid, which is defined by the normal vectors. Okay? So if it's central, we're going to do this argument. If it's not central, you can do basically the same argument with a little bit more care. Okay? But okay, so you apply the induction hypothesis to both of these arrangements. And then you remind yourself that the rank of the leading H is the same as the rank of A, as long as H is not a co-loop here. So let me first do it for H not a co-loop. So if H is not a co-loop, then this is the same thing as the rank of A. And the rank of the contraction, remember that here the arrangement actually drops one dimension. This is an arrangement living in hyperplane H. So actually when you do this, the rank drops by 1. Okay? And so what you get is minus 1 to the rank of A times characteristic polynomial A deletion at minus 1. And then you get a minus sign because here you have an extra minus. And you get the contraction. And now the point is that we showed that regions satisfy this recursion, but we also showed, the last thing that we showed last time is that the characteristic polynomial of M is exactly the one of the deletion minus the one of the contraction. So this is minus 1 to the rank of A times the characteristic polynomial of M evaluated at negative 1. Okay. So this is how you do it. The point is that we already did the hard work improving this recursion, and now you just have to check the details. This is for H not a co-loop, and if H is a co-loop, then you just repeat the argument and see that with very minor changes, the same thing works. Almost the same proof. That proves the first formula, and then again, if you want to prove the second formula, the argument is basically the same, because we also showed that for the number of bounded regions, we have the same recurrence. The bounded regions in A equal the bounded regions in the deletion plus the bounded regions in the contraction. So that's it. So we did all the work, and now we get Zaslavsky's theorem. Okay. Any questions about that proof? So that's a proof, but maybe it's not the most satisfactory proof in the world, because I proved that this statement is true, but I don't think we know yet why it's true, or where this formula comes from, or how did Zaslavsky think of this. And so what I want to do, I think for the rest of the class, is actually give you a completely different proof of Zaslavsky's theorem. And so what we're going to do is prove it again using some topology. And this proof will be, it will require a little bit more machinery. So we will need a little bit of topology, which I will explain to you. The advantages of this proof is actually, the theorem is just going to fall out of the argument. So a topological proof of Zaslavsky's theorem. So first let's learn a little bit of topology. So some topology. And I know that for several of you, this is the first time you see anything about topology, so feel free to stop me if you have any questions about what I'm going to say. I'm not going to prove anything, but I'm just going to tell you some things that are true about topology and give you an idea of how you use these things. So let's say that you start with delta, which is some topological space. Okay, and I'm going to try to avoid big words as much as possible, and so you can forget the word topological if you want. Just think of a space. So a space might be three-dimensional space. A space might be the surface of this Snapple bottle. Space might be the blackboard, whatever, some space. Okay. To this space, you can assign a number. And this is called the Euler characteristic. The Euler characteristic of this, you write it chi of delta, and this notation is very unfortunate for us because characteristic polynomials are also called chi. So I want to tell you that this is the notation people normally use, but it'll be way too confusing if I do that. So I'm just going to call this Euler of delta. Okay. This is going to be some number. Now, what's the idea here? The idea is that topologists study topological spaces, and they want to know if how to tell two spaces apart from each other. So it's that dumb joke about topologists that they're the people who can't tell their donut from their coffee cup. And the idea is that topologically, a donut is the same thing as a coffee cup. You can here's a donut. Here's a coffee cup. And the idea is that these things are very different to a normal person, but not to a mathematician, because you can degenerate this shape and make it into this one. This one has one hole. This one has one hole. But you can take this one, and if you make this one out of Play-Doh, you can kind of continuously morph it to get this shape. And so these two things are the same. This is the intuitive term, and the real word, the mathematical term for that is homeomorphic. It basically means that the two shapes are basically the same. They're just kind of distorted versions of each other. So if I want to show that two things are homeomorphic, well, that's not too difficult, maybe, because I can just show you. Take this one and do something to it and get this one.
Actually, that's harder than usually, isn't it?
Or maybe it's just a little. No, in some cases it's.
In some cases it's easy.
In some cases it's easy because you can just say, okay, deform it in this way.
Yeah.
Okay. Maybe what I'll say is not that it's easier, but at least it's more direct.
Yeah.
You can kind of, with your hands, say this is what you do. But how do you prove that two things are not homeomorphic? You have to prove that there is no continuous motion that transforms this guy into this guy. And that's maybe a subtler question that really requires some background. And so one of the facts about this number is that this number doesn't change when you move continuously.
Yeah.
So this is a nice fact, is that if two spaces delta and delta prime are the same, where by the same I mean homeomorphic, or if you know some topology, you can even say homotopic, which is a weaker version of two things being the same. The point is, if two spaces look the same, then they have the same number.
Not the other way.
Not the other way around. So you could have two things that have the same number, but are not the same topological space. But this is an amazingly powerful tool, because it tells you, if you know how to compute these Euler characteristics, and if you want to know if two spaces are different, well, if you can just compute their numbers and they're different, then you know the spaces are different. So this is what's called a topological invariant. It's basically some evidence that two spaces really are different from each other. Okay? And this is really what all of algebraic topology is about. Is you take two spaces and they're very difficult. You can't tell them apart. And what you do is find characteristic of them that you can actually compute and maybe check find topological invariants. In other words, functions like this. It could be a number that you associate. It could be a group that you associate. The point being, it gives you some evidence that two spaces are different from each other. So this is, in a nutshell, what the Euler characteristic is about. Okay? And for example, you could take a soccer ball and a bowling ball. Okay. Are bowling balls filled? They are, right?
Yeah.
Yeah. So the soccer ball is empty inside.
It's got holes on it, though. A bowling ball.
But it
doesn't really matter.
So it has three holes.
Solid.
It's
All the way through.
But a bowling ball is solid all the way through in the
those
inside,
holes are just
except for these three holes. And continuously, you can just push the holes up. So
Okay.
the holes are irrelevant to the topology. Okay? But the point is, okay, so this is a soccer ball. This is a bowling ball. This is full. This is empty. And the question is, are they the same topological space or not? Can you take a bowling ball and somehow morph it and get a soccer ball? Get topologically a soccer ball. And you might, what do you think?
I don't think so.
You don't think so? Yeah? I don't think so either. This guy's empty, this guy's full. I don't know how you're gonna make a hole where there isn't any hole. But weird things are true in topology.
What if you were to take the center of mass and just expand it out till it became very thin shell?
Well, of course, the key question is, what does homeomorphic actually mean? What do I mean by a continuous motion? And you'll see that if you just kind of try to, out of the center, just make a hole, you're going to see that that's not a continuous motion. But there might be some strange continuous motion. And there are strange things that happen. For example, you can take a soccer ball and continuously turn it inside out. Yeah. And not use soccer balls have a little needle, right? Imagine a ball that is just completely solid on the outside, but has a hole on the inside. There is a continuous motion and there's a video for this. It's really crazy how they do this, but they just kind of twist it around, they do some weird thing, and they just turn it inside out continuously, which no one would ever think is possible, I think. I wouldn't think that's possible. And so that might make you think about this twice.
Federico, you mean with like a real soccer ball?
Can I bring the real soccer ball for you?
I don't think anyone has done this in practice, but
Don't try this at home with your own children.
that could be a good final project. But okay, so these two things, are they the same thing? Well, fortunately, so the first thing you could try is, do they have the same Euler characteristic? And it turns out they don't. The Euler characteristic of this guy is 2, and
It's hard for us to contradict you.
and the Euler characteristic of a bowling ball is 1.
Are you sure those holes don't matter?
Yes. For the same reason the coffee cup and the donut don't matter.
They're
Make
the holes in a bowling ball are exactly the same as the hole of the coffee cup.
Just stick your thumb in.
This
They don't go all the way
depends on
through.
what happens on the inside.
No, but really, it's just like if you took your three fingers into a ball of Play-Doh and you just push them in, but they don't join inside.
They don't join.
No.
They don't join inside. If they joined, you would be in trouble. Maybe, yeah,
But
they
they
would be
don't
in trouble.
join.
But they don't join. Okay, question, how do you compute this number? So, I haven't told you what this Euler characteristic is. So definition / theorem. what you have to do is this. You have to, the Euler characteristic basically tells you if you have a complicated space, you cut it into pieces that look familiar to you, and then the Euler characteristic kind of keeps track of how they fit together. So if you take a topological space, and what you do is that you decompose it nicely into nice pieces. So what notation did I use here? You decompose it nicely into nice pieces. Okay. Of course, there's topological words that go here. What does nicely mean? What does nice mean? Intuitively, this means like bowling balls. I mean, it's kind of solid things, solid patches of a certain dimension. But for example, it's not a nice piece to have something with a hole. So a soccer ball is not considered a nice piece. But a solid blob of 3 dimensions or a solid patch of 2 dimensions or in 5 dimensions, those are good pieces. Say, and these pieces are called cells. Say there are Fi cells of dimension I. Because when you cut up your space, you're going to get maximum dimensional things, but you're going to get smaller dimensional things also. Then the Euler characteristic is defined to be the number of 0-dimensional faces minus the number of 1-dimensional faces plus the number of 2-dimensional spaces, so on. That's the definition of the Euler characteristic of the space. Okay. But what kind of a definition is this? I mean, this is a function of the space. And I said, okay, cut it up and do something and get a number. But how on earth would I know that different decompositions are not going to give me different answers? And a priori, there's no good reason for you to say, oh, well, of course this number doesn't depend on the decomposition. But so the theorem part of this is that this doesn't depend.
I mean, that comes
On the decomposition.
That comes before that fact, essentially. If you already know that fact, then
Sure. Sure. But maybe instead of going somewhere abstract, I think we should just do an example. So how do you compute the Euler characteristic of the soccer ball? Let's do that one. So let's stop calling it a soccer ball and call it a sphere. Okay. Hollow sphere. Well, we have to cut it up into pieces. So here it is. It's hollow. And so right now, I have only one piece, but that piece is not good because it has a hole. Okay? So I need to at least make one cut. So what cut would you make if I forced you to make a cut?
Cut it in half.
Just cut it in half. Okay, and so now I have two pieces, the top cap and the bottom cap, and a third piece, which is the equator. So that's what I was telling you, that when you make a cut, you get lower dimensional pieces because here you have the two-dimensional upper hemisphere, northern hemisphere, the two-dimensional southern hemisphere, but then their intersection is the equator, and that also counts as a cell. Okay. Now, is this a good decomposition or not?
Not yet.
What do you guys think? The equator is the kind of troublesome here because the equator still has a hole. And I said I'm not allowed to have holes. If I'm going to have a one-dimensional piece, it should just be a segment.
What's the third piece again?
So upper hemisphere, the lower hemisphere, and the equator.
Like a little ring?
The ring, yeah. So this is a two-dimensional piece, and a one-dimensional piece. But this is no good because it has a hole. So we have to make another cut. And I think that maybe the next natural cut is just to make another slice. Okay? It's an orange, I don't know. So let's make a slice like this.
So when you make your second slice, you're slicing your original object again,
Mm-hmm.
and then seeing what it does to everything.
Mm-hmm.
You can't
I mean, really,
chop up the individual pieces.
I'm just saying what are the pieces of this decomposition? How many two-dimensional pieces do I have?
2, 3, 4, 5, 6.
Two-dimensional pieces.
2-dimensional.
Well, basically, I have this one, this one, this one, and this one.
Yeah.
4. And I basically just took an orange and cut it into 4 pieces.
Mhm.
Actually, apples are the ones that you slice like this. Oranges kind of come with a slicing already.
Sorry,
Yeah.
this is a hollow sphere, right?
It is a hollow sphere.
Why is the northern hemisphere two-dimensional and isn't three-dimensional?
No, because it's hollow. So there's
Oh, yeah.
so the interior is empty.
It's embedded in 3 dimensions
Sure.
because of how it's curved, but
Mhm.
it's a 2-dimensional.
It's a two-dimensional space.
Yeah.
So I have, so this wasn't good. Okay, but now I have 4 pieces. Four two-dimensional pieces. And those look all right. They're really just patches, two-dimensional patches. How many one-dimensional pieces do I have?
4.
Well, here there's kind of a division point, and so what I get is 2 equators, and each of the equators cut in half. So you have something like this, something like this, something like this, and something like this. So you have 4 one-dimensional pieces. And how many zero-dimensional pieces do you have?
4, 5, 6.
And first of all, are these pieces okay?
Yeah.
They are. They're just segments. I mean, they're bent segments, but they're just solid segments. Zero-dimensional pieces are these 2 vertices. So, and those are also fine. And so what's the Euler characteristic? It's the number of zero-dimensional pieces minus the number of one-dimensional pieces plus the number of two-dimensional pieces.
So the lower dimensions are basically intersections of the higher. That's the only way to do it.
Right, so the lower dimensional cells are basically obtained as intersections of the higher dimensional cells. But again, this is where topology can get strange and do strange things. And so the complete answer to this question is that I have to really tell you what is a nice decomposition. But intuitively, that is what it is. The higher dimensional things are the main slices, and the lower dimensional things are just where the higher ones
It's
attach.
also assuming that you started with a nice space. You couldn't
And
have
you-
just
Nice topological space.
something, some weird curve sticking off of your sphere for some reason.
That's true. So only for nice topological spaces can you do this, but almost everything that you encounter in you can do this too. Chris.
So we would do the same thing with the bowling ball. We wouldn't have to cut it at all, right? It's just a nice piece to begin with.
Exactly. So for the bowling ball, then the first piece is already nice. There's no cutting to do. And so what's the Euler characteristic?
1.
0 minus 0
Right, minus 0 plus 1.
plus 0 minus 1.
Minus.
No, it's 1, and again, there's just some subtleties here, but it's 1. Because the point is that, yeah. Anyway. I don't want to go into too much topology. Basically, this is just a vague idea of what these things are, and things are really very interesting, and it's a very interesting course that you should definitely take one day. Next semester, for example. Is it offered next semester?
Supposedly there's a 450, which is just a 0.7 topology.
Yeah, so this would really be a course in algebraic topology.
Which is being offered now, so it probably won't be offered again for 2 years or something.
So you should fight for it to get offered, because it's a very good course. And we're going to... Okay, so let me just prove Zaslavsky's theorem for you. See if I can draw something that makes sense here. So let's say, for example, that you're going to prove this for maybe the three-dimensional case is one that we can visualize. Okay. So let's say that you're living in R3. So maybe our arrangement is in the whole space. And let me just, to make things concrete, let me just look at the slice. Let me just assume that this one, the board is one of the planes in my picture. So this is a three-dimensional arrangement, but this is one of the flats in the picture. Okay. So there's other things going on here, into the board, out of the board, into the board, out of the board. This is just a slice of the arrangement. So a two-dimensional slice of an arrangement in R3.
Yeah, you can do that. I think since they're all linear, you can just kind of choose any one of them, any one hyperplane, and look at it.
But actually, I'm gonna prove this even if it's not linear. So this is gonna be a proof that does not assume linearity. So what I'm saying is really that what I'm doing is intersecting with one of the flats. Actually, I should say that because this is one of the flats of the poset. So this is really one of the hyperplanes in the poset along a flat F. So you have your higher dimensional thing. A flat is some subspace that lives inside there, and you're just going to look at what the other hyperplanes do here. In other words, the board is one of the planes in your arrangement, and these are just the intersections of the other ones with the board.
So there could be guys out here that are parallel to it.
There could be another hyperplane here parallel to the board,
Yeah.
like the back wall.
Sure.
That one just doesn't appear in this picture. Okay. How does this look in the intersection lattice? Actually, it's not a lattice anymore if this guy is not central. But the intersection poset looks like this. Well, F is over here somewhere. But there's other hyperplanes. There's many hyperplanes. Okay. The bottom is all of R3, right? Then the planes, one of the planes is F. And then what flats do I have here? Well, I have a bunch of flats. So let me give these guys names, and let me match it to what I did here. So let me call this line G1, G2, G3, and G4. So these are flats that are contained in F, G1 up to G4. I have other flats, which are these points right here. Let me call these H1, H2, H3, H4. So these are maybe over here. H1 through H4. For example, H1 is the intersection of G1, G2, and G3. And then it's like this. Okay? And so of course, the lattice is some big thing, and I'm just looking at this. Looking at the slice of F corresponds to looking at the things above F. So really, I'm just focusing my attention on this, even though the intersection poset is some bigger thing, some bigger thing. Okay. Okay, so now let me do this. Well, you see, I can do some topology here. I can do topology over here, because here I have a space, topological space, F, and I naturally have it cut up into nice pieces. So what can I say? I can say that so F is decomposed nicely. And the Euler characteristic of F is just going to be the F0 minus F1 plus F2, so on, for this decomposition.
Just plus F2 here, though.
Now,
But
in general, you have dot, 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 but F is only two-dimensional, and so you only have zero-dimensional, one-dimensional, and two-dimensional slices. Okay. How many zero-dimensional slices do I have? In that picture, I just have 4, right? You see them.
Yeah.
And each one of them corresponds to one of the flats here. So somehow, one of them comes from H1, one of them comes from H2, one of them comes from H3, one of them comes from H4. These are the zero-dimensional things. Okay? And you'll see why I'm writing it like this. What about the one-dimensional slices? Well, I have a bunch, right? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Each one of these segments is a nice slice. But what I'm going to do is say, well, look, these 3 slices right here, this one, and this one, are actually the regions of the arrangement in G3. I mean, G3 is a plane. I have a hyperplane arrangement in G3, which is point, point. And these guys are just the regions inside G3. So I want to say that this is just the number of regions inside G1, number of regions inside G2, regions inside G3, regions inside G4. So the regions inside G1 are this one, and this one. Inside G2, this one, and this one, and this one. Inside G3, this one, and this one. Inside G4, this one, and this one. So I count each one of the pieces, and I don't overcount. And this is why I wanted to just write it like this, even though it's a little bit silly in 0 dimensions. But I'm just going to think that each one of these points accounts for one region, which is just the region H1, the region H2, region H3, region H4. What about the two-dimensional things? How many of those are there? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But instead of counting them by hand, I can just say, well, look, these are exactly the regions of my arrangement F. Okay. And so the Euler characteristic is this guy minus this guy plus this guy. And does this remind you of something? Here I have a function of a flat. The function of a flat is given by regions in here minus regions in here plus regions in here. This is exactly Mobius inversion, where Euler of f is one of your functions, and you're just adding up on top of the posets. What am I saying here? I'm saying that the Euler characteristic of f is you get one summand for each one of the flats above f. So for each g above f, you get the number of regions of g. And you get that, but you get it with a sign. Right? And what is the sign? It's negative 1 to the something. And what is that something? Well, for the 0-dimensional flats, it's 1. For the 1-dimensional flats, it's negative 1. For the 2-dimensional flats, it's 1, and so on. So it's just the minus 1 to the dimension of G. If the dimension is even, then you get pluses. If the dimension is odd, you get minuses. So this is really just the definition of the Euler characteristic of F. Okay? And it just calls for Mobius inversion. You'll get used to this when you count. So whenever you see something like this, you just immediately apply Mobius inversion. Mobius inversion says I have two functions. Here's the first function. Here's the second function. The first function is obtained by adding over the g's bigger than f, the second function. So you just invert this relation, and you get that minus 1 to the dimension of f times the number of regions of f is the summation, where again you add up over the g's that are bigger than f. Now you add up Euler of G, and the number you're supposed to put here is the Mobius number. Okay? And what you see before your eyes, even without looking for it, is a formula for the number of regions in a flat. Now, what is it that we're looking for? We're looking for the regions of the arrangement. Okay? This tells us what are the regions inside a given flat. So if I want the regions of the arrangement, what am I supposed to do here? Well, for example, the regions of F are these two-dimensional things. But if I want the three-dimensional regions of this three-dimensional arrangement, then what I have to do is find the regions here. The regions contained in R3. So all I have to do is plug in F equals bottom element of the poset, which is R to the, what did I say I'm living in? R to the n. So what do I get? I get minus 1 to the dimension of F is n times the number of regions of the arrangement is equal to summation for G bigger than F. But F is the bottom element, so everything is bigger than it. So I add up over all G in the intersection poset. Mu of G. I get mu of 0 comma G, which is the same thing as mu of G. And the Euler characteristic of G. Okay? And so I almost have the formula that I want. The only thing is that I don't know what the Euler characteristic of G is. And do I have... I don't think I have time to prove this to you. But, I mean, of course, once you get to this point, if you don't know what this Euler characteristic is, you just find the nearest topologist and ask them. They'll tell you. The Euler characteristic of R to the D is minus 1 to the D. It's actually a good exercise. You should do this. So this is just summation over G in the intersection poset, mu of G times minus 1 to the dimension of G. And this post-it is graded by dimension. So that the three-dimensional things are in the bottom level, the two-dimensional things are in the next level, and so on. So the number of dimensions is the number of floors from the top. Three-dimensional things are 3 floors from the top, and so on. The d-dimensional things are in the floor R minus D. So this is just R minus the rank of G. And this is just by definition the characteristic polynomial evaluated at negative. And so here you just get the formula falling out of the sky, you know. It just happened that you got this formula. Any questions about this? This gives me a second proof of this formula. Now I think it's actually worthwhile to talk about this. What about this second formula? Let's say that you want to derive the formula for the number of bounded regions. The question is, can you just do the same thing? Well, basically the regions appear here. So if in this formula over here, you can also find a nice formula where instead of regions, you get bounded regions, and you can express this as a nice Euler characteristic, then everything is going to work just fine. So what if I wanted a formula that instead of regions had bounded regions here? What Euler characteristic am I computing with this expression? I'm just looking at the bounded regions in this picture, which means I forget the ones that go off to infinity, and I just pay attention to these guys right here. Okay. The bounded regions of H1, H2, H3, H4, minus the bounded regions of the lines, plus the bounded regions of the arrangement. This computation is exactly the computation for the characteristic polynomial, for the Euler characteristic, not of the whole space, but of this bounded piece. So this is the Euler characteristic of what you might call F sub bounded, which is the union of the bounded regions. Okay? And so, you can just do F sub bounded, G sub bounded, G sub bounded, and now the question is, can you compute this number? If you can compute this number, you're going to be finished. You're going to get the formula for the bounded regions.
And then those guys will become B's.
These would become B's, exactly. Exactly. This would be a B. 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 And now you are only left with computing the Euler characteristic of the complex of bounded faces. And so again, even if you didn't want to do this, you're going to have to study the topology here, because the topological question is: I give you a hyperplane arrangement, you look at the bounded faces, and I ask you what is the Euler characteristic of the bounded faces. You're stuck studying that topological space, even if you didn't want to, if you want to make this work. And this is what people did. And actually, this is and so the question then is, what is the topology of bounded of the bounded faces? Really, what you want to show is that the Euler characteristic is equal to 1. You'll see that if you show that, everything works. And And so people were wondering, why is this Euler characteristic equal to 1? If you know some topology, when an Euler characteristic is equal to 1, you might hope that this space is so nice that it just contracts to a point, like the sphere does. That's why the sphere has characteristic 1, because everything that collapses to a point has Euler characteristic 1. And so the natural question was, is this true here? Can you...
Wait, you mean the ball?
A ball. Did I say
You
sphere?
said sphere.
A ball. So a ball has no holes, and you can just smush it into a point.
Sphere has characteristic 2.
Sphere means with a hole. Here, if you look at this space, it looks like a two-dimensional ball, which you can squeeze into a point. And the question people wondered is this true for any arrangement? This problem was open for many years. And actually, only... I wanted to give you this as a project, and actually someone just solved this a few months ago, in November. They just showed that...
It's still a project.
They just showed that that it is true that this thing is homomorphic to a ball for nice arrangements. Okay. So this is really some nice recent results. And by recent I mean from November of 2006. And so if you're interested in this kind of thing and you know a little bit about topology, this is something else that you might think about, and there's some really nice stuff there. All right, that's it.
So I'll just come up at 4 and see if you're here still.
I'll actually be here.
Oh, you'll be down here? Okay. Because there's the continued fraction thing from 3 to 4, which I guess is probably upstairs.
Good question.
Yeah. So I'll just... Oh, it's not today? When is it? Oh, there is not.
Next week. These come in.
Okay, so you have a meeting from 3 to 4 then? I guess I'm free at 3, but you are not, right? All right. Was what? Oh, yeah, I'll try to find it.
I know, but knowing the answer never. My high school physics teacher liked teaching that way.
Are you going? Do you have office hours right now?
You'd say, you know
I
the
have
answer.
office hours too, but I can.
Leave a note on your door saying, come find me.
I can tell the other people in the office that I'm. Right.
Your office in Thornton?
Yeah. It's just on the other wing. No, it's always been. It's on the other wing.